So today we have a rather succinct talk, but quite a meaningful talk within the with regards to CK and Bitcoin and some of the stuff that we've been doing very recently at QED. So today we're going to be talking about symbolic execution and its role in making it really nice and easy for us to build compilers for both CK and Bitcoin. So if we look back to some of the stuff that we may have learned in computer science. So kind of a throwback to some of the uni days for us. We may remember binary expression trees. Anyone in the chat remember binary expression trees from school? But essentially the rule is we can build this tree by parsing the syntax of some expression. Like over here, we have 5 plus z divided by -8 multiplied by 4 to the second power. And the rule is we evaluate from left to right, bottom to top, right? So in this case, we add 5 and z, and then we divide by 8 times -1. And then over here, we're going to be multiplying by, well, what are we here? We need to start. We go all the way down to our 4 to the second power, and then we're going to multiply that by 16 and get our result, right? So we can use these binary expression trees to evaluate some arbitrary expression. And the great thing is that when we're dealing with things like zero knowledge proofs, this actually is something that we're very familiar with. In fact, it's an arithmetic circuit, right? So the output of the arithmetic circuit is on top, and here we have the inputs on the bottom. So we've developed a framework called Symbolic that helps you generate these parsers very easily for TypeScript-based programs. So let's get into it, and then we're actually going to do a little bit of a source code tour. But yeah, so Symbolic is a framework for generating and evaluating code. It supports TypeScript and JavaScript. And the cool thing is that it lets you emit your own code as you're evaluating and also test the evaluation within TypeScript so that you can really quickly see whether or not your code is working. So let's get into that. So maybe I can first get out of here. Let me hop back to VS Code real quick. Cool. So over here, I'm not sure. I'm assuming probably everyone in the chat is reasonably familiar with TypeScript, hopefully. Yes, no, you can let me know in the chat. But yeah, so over here, we actually have a U64 evaluation space. So if you're building applications that are going to be using like, let's say the Goldilocks fields for zero knowledge proofs, it's a great place to start. But in this case, we're using it for, I'm not sure if anyone here is familiar with Liquid Bitcoin or the Liquid series of chains that uses the Elements project, which is a fork of Bitcoin Core that is developed by Blockstream. But over here, yeah, we've defined some operations, right? So we have like add 64 carry, subtraction, multiplication, and so on for 64-bit integers. And what we're going to do is we're going to generate an evaluation trace based on some programs. So with Symbolic, it makes it really, really nice and easy. So over here, we have our program. So what we're going to be doing is we're going to be defining several inputs, and we can define those by using the add input function. And then we can perform operations like here we're performing the add 64 carry, which is going to add 2 numbers together, and it's going to return the sum of those 2 numbers as well as the overflow bit of that addition operation, right? Because if I add 2 numbers, like let's say, I don't know, if I were to add like, let's say 1n to the 64n minus 1n, oops, over here, which is like 0x f string 16 over here, right? If I add these 2 numbers together, it's going to result in an overflow bit being emitted. So if we look over here, if we look at the addition result, and we take that and this number over here, we can see that we have the remainder here, which is going to be 1 bit less, or it's going to have that upper bit flipped positive, whereas the lower bits are going to be remaining. So if we convert this to binary, we can see the bit string there. And if we and 64 bits. So now we're going to limit it to the bottom 64 bits, which is going to be the result of that addition. And we convert it to binary rather. Then we'll see that, in fact, the string is as we predicted. Whoops. There we go. We can see that, in fact, the lower addition is just the lower 64 bits with that single bit carry. And so that single bit carry is just going to be in the carry there. And if we actually look into our implementation, we've defined both a code generator, which can emit code. So in this case, we have this op use, over here, we have this op u32x2 add carry, which if we hop over to bit ID in a second, we'll see how that's actually defined. We've defined an implementation which can allow us to calculate on the fly, so we can get an evaluation from our symbolic. You can think of it as your binary expression tree. We can evaluate it within the program because we've defined for a given node within the tree what it means to do an addition, right? And then in addition to that, no pun intended, we also can emit some code which performs the operation. That way, we not only have a way to generate a symbolic evaluation of the program, but we also can compile it to, if we're working with, let's say, in the case of a zero-knowledge circuit, we can compile it to rank 1 constraints. Or in the case of Bitcoin, we can compile it to a bit IDE instruction, which performs that operation. And we can actually emit that code and therefore generate, a nice, let's say a nice implementation trace for our function that runs on Bitcoin. So let's do that. So let's hop back over to the PPT and let's get into it. So again, in this case, we've defined a Bitcoin VM core generator that's compatible with bit IDE. I'm not sure. I believe have we done a presentation on bit IDE in the past on and alpha? I don't think so. So it might be rather new for some of the folks, but it's a next generation, Bitcoin IDE and editor. We have lots of education resources on that, but main thing here is we can emit Bitcoin VM code from a compiled TypeScript program. So yeah, Symbolic plus bit IDE is a big win. And just like brief introduction of bit IDE. So bit IDE is just like this scripting environment for Bitcoin that we're going to be using that solves some of the major issues with Bitcoin. Really, like I guess on the opcode side, it's quite limited as far as Bitcoin VM goes. And in addition to this, a new release that we've made from the QED team is we actually most recently supported Liquid as well. So we're going to be going through that. That's a brand new release on our end. Liquid is a great Bitcoin L2 for anyone that's looking to develop on a Bitcoin L2 as well. So bit ID is there for you if you want to try it out. But again, if anyone wants to follow along, we can just hop over here and do Docker run. And we're going to pop open with bit IDE. I've actually already got it running here. So in previous tutorials that we've done on bit IDE, we run the bit IDE and then just, colon latest. But if you want to support Liquid or test out our Symbolify demo, you're going to want to do -liquid again if you're following along in the chat. So let's get into it. So over here, we have our nice bit IDE program. And what we're going to want to do is we're going to want to go over here and go to our program. And now we can tweak it around. So over here, we are, let's see over here. So if we look over at our BTC test, we're doing an add 64 carry and then a multiplication that's going to return high and low component. And we can actually see what that actually looks like in our IDE implementation. So over here, we've defined a liquid compatible. If we look over here, we've set our VM mode to liquid, a liquid compatible 64-bit multiplication for high and low numbers. So just really quickly, we can show a little demo of that for those that are following along. Let's see here. This one should be okay. Yeah, so over here, we can do our multiplication, high, low, and let's just remove the check result for fun. So we can multiply these 64-bit numbers, and we're testing out this instruction which if we go back to Symbolify, is going to be emitted every time I perform that mul64 high-low operation in our script. So again, you can define your own operations, and we're going to define a new one quite shortly, but let's get into it. So if we go over here and go to run script, we can see that in fact, these two numbers multiplied by each other. Let's go ahead and do a quick sanity test to make sure that we're getting the right result. If we multiply these two numbers by together, this is going to be the result. And if we convert it to base 64, you can see what the hex of that is going to be. Whoops, 16 rather, not 64. And we can see that we've indeed got this limb decomposition of 7.3 FDA 848, which matches up over here, 7.3 FDA 848, looking good. Then we have the next, then we have the next, and then we have the next, right? Now, in bit IDE, we need some way, of course, of handling these four elements. And normally, with previous instantiations of bit IDE that we've demoed, you kind of have to manage the stack on your own, right? But we want to be able to compile these TypeScript programs into Bitcoin assembly, in this case, using Symbolify. So how do we actually do that? Well, let's go over here and see how we handle it. We can see over here, we've defined return layout so that you're returning two limbs in our symbolic execution. So again, if we go back over to our BTC test, you can see that we're returning a product high and a product low. And those are two 64-bit numbers, right? So we return the high 64 bits and the low 64 bits. But if we look back at bit IDE, we're actually returning four numbers, right? So how do we deal with that? Well, we define a return layout in our code emitter. So if we go back to our operations, we can see that the return layer is defined as 2 and 2, right? So we're going to return two what? 32-bit numbers, right? And then two other 32-bit numbers that are going to represent the high and low 64 bits, right? So if we go over here and we can, play with our code, let's just go ahead and do a very, very basic demonstration. I don't know, we can just, let's say we remove this third input, remove this guy, and we're just going to return the product high and low. So let's go input 1, input 2, and then let's do builder.add outputs. So now we're going to add outputs that are going to be emitted by our code function. And let's just put in, I don't know, let's put in the lower 64 bits, let's say. Right, followed by that. Why is that saying that? What's going on here? Add outputs. Sorry, I missed that there. So if we go here and we compile our code, npm build start, we're going to see the actual Bitcoin VM script emitted over here. Oh, whoops, we got to save that first. So we can see the actual Bitcoin VM script compiled over here. So if I go back over to our script and we say, and we replace this guy over here with that, right? And we compile, we can see that we get the same result. Now, if I reverse the outputs, it should reverse those two limbs there. All right, so let's give it a try. And now we can go ahead and copy and paste away. Oh, whoops, I think I forgot to save again. Let's see here. There we go. And if we, oops. Now run our code, we can see that the outputs have indeed been reversed. So now we can add in some more complicated features, like over here, we add in some additional additions. So if we go back to our old original script, we're going to be, what are we going to do? Well, we're going to take the first two inputs and we're going to add them together. And then we're going to multiply the sum of those inputs, so without the carry, by input 3. And then we're going to add the two limbs, so the upper 64 bits and the lower 32 or in the lower 64 bits together, and we're gonna emit the low product, the high product, and then that sum. So we can go ahead and do that. And if we go here, we can see the result that we're going to want is we're going to want these three 64-bit numbers as our output, right? So let's go over here. And we can hop into this demo over here. And we can just paste in our code, directly from Symbolify into our bit IDE, of course. And click run start. And let's see if we got the right answer. So we're looking at, let's see what we got here. So we've got 2EF64. What is that going to match up with over here? Let's say 2EF64. This is looking good, right? And then we've got our 36008430, which we do see over here. So looking A-okay. And then indeed, we also have our 68175, 68175. So you can see that we were able to actually compile this TypeScript code into a functioning Bitcoin script, which again, has been done on Bitcoin SV in the past, but has never been done on initial Bitcoin. So now we can say that we can write these smart contract-like scripts, or scripts written in human readable code, for Bitcoin that run on Bitcoin VM today on Bitcoin Core. So very exciting stuff, of course. Now, what else can we do with our wonderful, symbolic execution engine? Well, we can do some vastly, vastly more impressive things. So if we go over here and we hop over to one of these bitwise examples, should be this one, we can see some much more complicated examples of things that have been compiled with our wonderful scripts. So let's go over here to the Blake 3 demo. So over here, what we're going to be doing is computing the Blake 3 hash of this very large, hex to U32 array, right? So how in the world have we re-implemented Blake, in Bitcoin script? So is anyone in the chat familiar with opcat or the Bitcoin VM at all? I think the topic hopefully would attract some Bitcoin folks, maybe in the chat, just so I can meter everyone's Bitcoin scripting prowess. Anyone in the chat? I don't know if can I see the chat? Any Bitcoin folks? No one's tried to, okay, so maybe we can hop over to, so we have this problem with Bitcoin, right? Which is that Bitcoin script can be a very, very powerful tool for us to build, sort of smart contract-like execution on Bitcoin, with one caveat, which is that if we look over here at the official Bitcoin wiki, we can see a bunch of instructions, but what do we have here? Disabled, 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 disabled. What does this mean? This means that even things like multiplication on Bitcoin, we can't do, right? So we don't have opmul, we don't have opcat. How in the world are we going to verify a Merkle proof on Bitcoin, right? Well, we can't do arithmetic, based hashing because we don't have opmul. We can't do, something like SHA-256 or Blake because we don't have like op or op XOR or even op and, right? Well, in fact, with bit IDE, it does allow us to do this. I'm sorry that maybe some of you are not familiar with bit IDE. Perhaps we should have done a little bit more of an introduction there. But yeah, so using our symbolic execution engine, we were actually able to re-implement a lot of these opcodes, and indeed generate a Blake 3 compatible hashing script for Bitcoin. So again, we're really, really happy to be like open sourcing all the tooling that went into making this stuff possible. But over here, you can see like, in production, running in Bitcoin Core, we can see the actual, emitted opcodes for Blake 3. And again, this is all really only possible. Like, no one is going to sit there and write this enormous Bitcoin script, right? I mean, it would be quite a nightmare, right? But if we actually check the result, just so you know, I'm not completely full of garbage here. Let's actually do the test. So we go over to Blake 3 online. Let's try it out. Give a hex, give a hash. So we're expecting that hash to output this value, right? Let's see if we got it right. So indeed we did. And if we change it a little bit, just so again, you know that I'm not full of garbage, let's make this FF, right? So the hash is going to be totally different. Let's try it. Give it a click. And we're looking for an expected result of 6E. Let's see over here. So by the way, these are the 31-bit representations of the hash. So if I convert this to a wonderful base 16, we can see the, okay, we've got the B, yeah, over there, 0B31FFFC. We can see that value there, if we raise this, or rather, if we OR this with the top bit 1, since the top bit of that is going to be a 1. So if we take this value, or what are we going to do here? We're going to say 1, shift it over how many places? Well, in fact, 31 places, right? And then we, of course, in JavaScript, we have to clear the sign bit. We're going to get this value. And if we take this and convert it to a 16 base string, we get, in fact, 0B31FFCC. So we've gotten our output there. So again, Symbolify is really, really cool for making these kinds of operations possible on Bitcoin. And we've gotten a lot of comments of people asking, like, how in the world have you done this? Like, how have you built all of these, some say, impressive applications on Bitcoin? And honestly, the answer is via symbolic execution. So again, we want to make all of the work that we've done open to the community, just so that everyone can take part. And again, I actually haven't shown you that I'm not full of garbage. So let's go ahead and do the test, see what we get. Is this indeed the result that we were expecting? Well, we're about to find out, and you can see that it is. So yeah, that is Symbolify. Again, so today, I guess, like, two big takeaways. So first of all, if anyone wants to build on Liquid Bitcoin, which is perhaps the most prominent Bitcoin L2 right now, I know there's a lot of talks about stacks and so-called BVM, but you can't really compete. I guess the only real competitors for Liquid that are out there is, of course, our own L2O consortium, which, if anyone is planning on building a layer 2 on Bitcoin, should definitely join up. Our most recent member is Starkware, so we're very happy to have them on board. So if you're planning on building an L2 on Bitcoin, definitely join up with L2O. But if you're not going to be verifying your proofs, like zero knowledge proofs on Bitcoin, then I guess the next best thing that you're going to want to do is use something like Liquid. So yeah, so that's why we built the ID for Liquid. That's why we're here. And yeah, I guess I'd like to open it up and see, does anyone have any questions at this point? Any applications that people are thinking of building on Bitcoin? Because ultimately, at the end of the day, I think right now there is a problem with Bitcoin where we don't have something like a central, Ethereum foundation to promote Bitcoin applications, right? There's no real help resources. And that's why I think for a lot of people, it's quite difficult getting started on Bitcoin. And yeah, I'm curious if anyone has any interesting applications that they think might be able to be built with something like Symbolify. But I will definitely leave the chats in, or the links in the chat for both Symbolify and, of course, our new Liquid Bit IDE. So let me just paste that in there. Anyone have any questions about symbolic computation? Yes, no, maybe so. Perhaps none. Okay. In that case, maybe we can hop over to back over to here. So if we did indeed want to like implement your own instructions for your own program, assuming you do want to make one, again, you can just implement a sim builder and go to town with it. So all you have to do is implement for the various operations that you've defined. But yeah, I guess that's what I wanted to share with the community today. I think maybe since it's a Friday, we didn't have too many people, but hopefully, our online viewers that are building on Bitcoin can check it out. This is how we were able to verify zero knowledge proofs on Bitcoin, and we hope that the community is able to benefit from it as well. But yeah, any questions?
感谢 Carter。
Okay, awesome. So yeah, thank you for everyone's time, and I hope everyone has a great Friday.
Yeah, thank you, Carter。
Thank you guys so much. Yep, take care all.
好，大家如果有什么问题的话，可以群里再问，到
可以
时候我们可以
随时问，
联系。
我们都在讨论。
对，
我也希
随时问。
望就是如果大家开发什么就是好的应用，可以用 TypeScript 写这个 Bitcoin VM script，也是希望就是如果有一些创新，都可以一起合作。
对，有什么联系？如果找不到本人，可以找我，到时候给你们推荐。
好，
好，再
好，
次感谢
感谢各位，
Carter。
非常感谢。
好，
好，拜，
好，那再见，
再见，
拜拜。
拜拜。